This is G485 Homework Booklet, Question 5. First of all, a definition. Define the farad. Since we're asked to define a unit, we answer in terms of units. So a farad is a coulomb per volt. Next, looking at the circuit, we can see a capacitor connected to a battery, and we're told that the switch is closed in order to charge the capacitor to 12 volts. We're asked to explain how the plates of the capacitor become charged in terms of the movement of charged particles. Always respond to what follows a phrase like "in terms of." I would call it a question clue. So it said movement of charged particles. We need to identify what they are. They are electrons. We also need to identify the direction in which they move. So they flow clockwise or from negative to positive. However, we need to be aware that they don't cross the gap in the capacitor between the plates. Instead, they're deposited on A and they are removed from B. Moving on, we have two fairly standard calculations. First of all, the charge stored on the capacitor, just following and substituting into the equation Q equals CV. And similarly, energy transferred to the capacitor, a half CV squared. Good idea to check what units answers are in. Sometimes they will put a prefix there, and you need to just make sure that your answer is consistent with the unit that you actually intend. The second part of the question is a little bit more challenging. So we are now told that the capacitor is connected with a resistor in parallel. And the first switch is opened, so that breaks the link to the power supply. And now the second switch is closed, so the capacitor will discharge through the resistor. We're told that the initial current is 3.24 microamps. We're now asked to show the value for the resistance of the resistor. Following the idea of initial current and the fact that resistance is always the ratio of potential difference to current, as long as we choose a pair of readings that belong together, we'll get the right answer. So the 12 volts is the initial PD across the capacitor, and the 3.24 microamps is the initial current. So putting those two values together gives us the correct answer of 3.7 times 10 to the 6 ohms. Next, we're asked to calculate the current through the resistor at a later time. The data booklet will just give you the standard equation for exponential decay with a capacitor. That would say x equals x naught e to the minus t over RC. We just have to adapt that to apply it for current. So in this equation we have the time constant RC, and we can substitute in the values for the resistance and the capacitance involved. You can work that answer out at this point, or you can just handle it carefully in your calculation here. So the current at a later time is the current initially multiplied by this expression here, and that gives us 0.059 microamps. So here's a situation where they have put a prefix with the unit, and you just have to be careful what number you write down here. Finally, we're asked to explain the effect on the initial current or the initial rate of discharge when a second resistor is connected in parallel. A number of logical steps to work through here. So what is the consequence of adding a second resistor in parallel? Well, that is going to halve the circuit resistance. There are two pathways for current to flow, so it's easier, and the resistance is halved. Now, since the time constant is the resistance times the capacitance, halving R would also halve the time constant, and that would be an alternative answer. Now the consequence on the initial rate of discharge. Well, the rate of discharge is current. Current is rate of flow of charge. So the initial current will be doubled because the resistance was halved. You could also say the rate of discharge is doubled.